Okay, everyone. My name is Rajshekhar Subhas Saudi. Presently, I am working as assistant professor in School of Mechanical Engineering, KLE Technological University, Hubli, Karnataka, India. My experience in teaching control system and mechatronics will be helpful in conveying the need for tools, how to use the tools, and so on. Let us start today's topic. In this video, my focus will be on why we need tool like MATLAB or any other. This is purely a engineer's perspective. So when I say tool, it is basically to assist. It could assist anyone as we speak. Basically, we have too many tools. Even calculator is one, screwdriver, a tool to assist. What is MATLAB? MATLAB is a software tool. So there are so many tools in industry or otherwise. I am trying to make you understand why to use a tool. So let us understand with few examples. This is an exploded view of an induction motor. This motor consists of subsystems. If you consider this motor as a system, then there are subsystems within this. Let us say this is one subsystem. This consists of so many subsystems again within this, like windings and so many. If I consider bearing, the bearing can have small balls and these other materials together will make a one subsystem. But if you ask in industry who manufacture bearing, for them it's a system, but for our product it's a subsystem. So if you have a system, you can have subsystem and subsystem to that, and so on. So what I am trying to make understand now is, say we want to improvise this motor for a particular requirement, or we want to build one new. In both the cases, can we take a new parts, join them, assemble them, and test it to see whether we get required output? Of course, to some extent in this case we may try to do it, but again it cost you money. Some deep pockets are required. But in engineering anyhow, we don't do too many trials and errors. That's not our job. We try to do it mathematically first, and then we try to go close to the value and tune it a bit. But however, if you do take too many subsystems and integrate, we may get an unexpected output. So how do you see that before in hand? So these are something that we can't deal. We need to test them. But anyhow, we have such tools are going to assist us. So let us see another example. So if I take this example where this is a satellite launch vehicle, which is a PSLV in this case, it says rows. Now if you see, there are so many subsystems, and if I have to change a component and test it, even a country like US or India or any other can't do it. That means you can't simply modify some parameter, test it, and by physically make one hardware and test it. You can't do it. directly, because you need certain confidence before you actually test that. Here you require a lot of confidence because crores of rupees are invested for one particular hardware. So if you see the success stories, in this case the continuous successes followed by one failure, this is mainly because of the separation issue. The separation of heat shield was not possible. Then it caused the satellite launch inside that system. Thereby the communication to the external world was not possible, and then it led to a failure mission. If you see these examples, what do you understand? After knowing where system failed, then we can go back to these subsystems which we know can fix these subsystems in the next run. Anyway, these are part of engineering design process. But you can also validate the software so that next time these cases are taken care in your software. Now if I see another example like pacemaker or ECG, this pacemaker goes into your body, and the probes actually goes inside your heart or above your heart, which will be used to keep your blood pressure, BP or heartbeats constant. So if this goes wrong, you can't operate on a human being again and again. If they are into a body, they should be inside the body for say long period like 10 years, 15 years and so on. So you can't afford to have a frequent failures. So these are the cases. You have to test them well in hand. So you can't test it on a real system. So even ECGs, and if something goes wrong in an ECG, and whole medicine that doctors give may not work because the ECG's result that they are seeing itself is wrong. So if you want to test them before in hand, you can use simulations. What is simulation? Simulation is basically not physical but a virtual software based. So what does it do? It basically reduces the risk involved in actual conduction of experiment. Say like in the case of pacemaker, you need not have to test it on a human body, or say in case of induction motor, you don't have to construct it. But risk, if I say if you are working as an electrical engineer and you are working with very high power and you don't want to test it on real system, so they are too much risky. So then first if you want to test there, you need to have a lot of confidence so that you rule out many of the things which are likely to have a failure. That's one point. And then the another point could be time involved. So you can't test it with a short time. You require huge time. But in a software, you just have to change the parameter and other stuff. It may take few seconds to few minutes or few hours and so on. So thereby you can reduce huge amount of time. And when I say cost, it is cost which is associated with the conduction of experiment. So you will save time because you lose nothing. Basically, if something goes wrong, you hardly restart your software, or you will see some wrong results. That's all. So now, why we need simulation? If you see this is a basically typical product life cycle. Any product start early in the market. It starts and then it goes to have a saturation, and then it starts declining. If you consider say any product, early, which are the first one who enters the market are innovators and then early adopters. If somebody enters after early adopters, then they will have a shorter time to sell their products, and once they start selling the products, already other people and market has penetrated and other peoples have already gained the profit and they can give stiff competition, thereby you are likely to have a tough fight. Once in a short period you are likely to have a decline in the sales, thereby you lose lot of money. There is no point in entering later. So if you want to be there, you want to sell your product, you should either be innovator or early adopter. If you want to be, say, innovator or early adopter, you should have basically R&D, research and development, goes before in it. If you want to have a better shorter R&D, then you can have innovator or you enter the cycle early. If you want to have a shorter R&D, then if you use simulation tools which can give you the result faster, and you can do too many iterations. So if you don't, this doesn't work, you change it, come back, this doesn't work, change it, come back. So you can do too many iterations and thereby you save a lot of time, cost and the risk associated as we discussed, and thereby time to market will be reduced. Thereby you can enter the market early. So this gives a broad foundation for you to know why the tools are required. So if you have any suggestions or you need more information, you can always comment on the video link. Thank you.